In the profound hush before the beginning, the fabric of the cosmos was untroubled by questions. There was only the silent promise of becoming, a tapestry not yet woven, threads of possibility stirring in a darkness so complete that even the concept of darkness was itself unborn. Billions of years later, on the thin crust of a planet circling an average star, minds of water and carbon would gaze up, searching for meaning in the night's cold brilliance, their questions as ancient as the light they received. What holds the universe together? What tears it apart? What, in all the infinity of existence, is the fate that awaits everything that is and everything that will be lost? For centuries, astronomers clung to the notion that gravity was the universe's master, the cosmic sculptor, binding galaxies, orchestrating the slow dance of stars, dictating the grand architecture of clusters and filaments. The expectation was simple and almost comforting. Gravity, universal and unyielding, would eventually halt the expansion set into motion by the Big Bang. The universe might slow, stop, and reverse, a cosmic breath, exhaled and then drawn back in, ending in a collapse as inevitable as sunset. But the cosmos, as always, keeps its most critical secrets veiled. In the late 1990s, when the Hubble Space Telescope's gaze pierced ever deeper into the ancient night, astronomers set out to measure the universe's rate of expansion with unprecedented precision, using the brilliant, catastrophic deaths of stars, type Ia supernovae, as cosmic yardsticks. These stellar explosions, uniform in their ferocity, were supposed to be beacons, their distances and brightnesses charting the universe's slowing growth. Yet what the astronomers found was not a universe slowing down, but racing away, accelerating. The galaxies were not being reined in by gravity. They were fleeing from each other faster and faster, as if some hidden hand were pulling space itself apart. This discovery landed like thunder. Saul Perlmutter, Brian Schmidt, Adam Rees, their names now etched into the annals of science, announced that the fabric of reality was being stretched by something utterly unknown. Something they called, almost apologetically, dark energy. Its name was chosen less for knowledge than for ignorance, a placeholder for a mystery as profound as gravity itself. In the years that followed, the numbers gathered with a relentless, impersonal certainty. Observations of the cosmic microwave background, meticulously mapped by Kobe, WMAP, and Planck, confirmed the universe's geometry, flat and therefore balanced on the knife edge between endless expansion and eventual collapse. But the visible matter, the glowing stars and swirling gas, accounted for less than 5% of the cosmic ledger. Dark matter, massive, invisible, yet gravitationally potent, added another 27%. The remaining 68%, that was dark energy, a presence everywhere and nowhere, dictating the destiny of all things. What, then, is dark energy? The question hangs over modern cosmology like the silence before a storm. The simplest hypothesis, and the one favored by the data so far, is that dark energy is the cosmological constant, L, first introduced by Einstein in 1917, as a mathematical curiosity, a fudge factor to keep the universe static. When Hubble showed that the cosmos was expanding, Einstein supposedly called L his greatest blunder, but the universe has a way of demanding humility. The cosmological constant is a property of space itself, an energy density that does not dilute as the universe grows. Every cubic centimeter of space holds a tiny, immutable amount of dark energy, and as more space comes into being, the total grows, fueling the acceleration. But if this is the truth, it is a strange truth indeed. Quantum field theory, the language with which physicists describe the vacuum, predicts a vacuum energy density so vast, 10^120 times greater than what is observed, that if true, the universe would have torn itself apart before galaxies, or even atoms, could form. This is the cosmological constant problem, a chasm between prediction and observation so vast that it stands as one of the greatest unsolved puzzles in all of science. The vacuum, seething with virtual particles and fields, should be an engine of unimaginable power, yet the universe is almost eerily still, its expansion gentle, its structure intact. Perhaps then, dark energy is not a constant at all. Some theorists invoke quintessence, a dynamic field that evolves with time, waxing and waning as the universe ages. Quintessence would be akin to the inflationary field that drove the primordial universe to expand faster than light, but far weaker, subtler, a cosmic ghost present everywhere but detectable only through its effects on the universe's growth. If dark energy is quintessence, its properties could change, and with them, the fate of the cosmos might shift, an acceleration that slows, reverses, or even erupts into something new and unexpected. Beyond these, wilder hypotheses abound. Some posit that dark energy is an artifact of our ignorance, a sign that Einstein's general relativity is incomplete at the largest scales. Modified gravity theories, FR gravity, scalar tensor models, extra dimensions, propose new rules for the cosmic game, each with its own predictions for the universe's fate. Yet the data, for now, remains stubbornly consistent with a simple, constant L. Still, the darkness is not empty. The acceleration of the cosmos, though imperceptible on human timescales, is inexorable. Over billions of years, the galaxies will drift farther apart, their light red-shifted into invisibility. The stars will burn out, the gas clouds will thin, and the night sky will grow ever darker, the tapestry unwinding thread by luminous thread. In the far future, only the gravity-bound islands of galaxies will remain, and eventually, even these will fade, their stars dying, their matter swallowed by black holes, until even black holes evaporate into Hawking radiation, whispers of energy in an endless night. Yet darker fates are possible, depending on the true nature of dark energy. If its density increases over time, a scenario called phantom energy, the acceleration could become so violent that it rips apart galaxies, stars, planets, and even atoms themselves in a final, catastrophic Big Rip. Alternatively, if dark energy decays or reverses, the expansion could halt, and the universe could collapse in a big crunch, a mirror image of its birth. There are scenarios of big freeze, big rip, big crunch, and even big bounce, each a possible coda to the cosmic symphony, each dictated by the properties of a force we barely comprehend. What then is the risk for the universe's future? Is there a peril in the acceleration, a hazard in the endless stretching of space? For human beings, the timescales are almost incomprehensible. Trillions of years before the stars wink out, quadrillions before even the black holes vanish. Yet the existential risk is not to minds or civilizations, but to structure itself. The ultimate entropy, the heat death, when the universe is cold, dark, and featureless, a sea of particles drifting in infinite silence. Still, the search continues. The Vera C. Rubin Observatory, the Euclid mission, the Dark Energy Survey, the Nancy Grace Roman Space Telescope, all are designed to map the universe's expansion with exquisite precision, to chart the fingerprints of dark energy across the ages. Each supernova, each galaxy cluster, each subtle distortion of light by gravity, the phenomenon known as weak lensing, adds another piece to the puzzle, another clue to the true nature of the force that will determine the universe's fate. In the laboratories of Earth, physicists attempt to probe the vacuum, to measure the Casimir effect, to seek out deviations from Newton and Einstein at the smallest and largest scales. The Large Hadron Collider smashes protons in search of new particles, new forces, new symmetries that might explain the cosmic acceleration. But the silence persists, the data aligning with the simplest story, the mystery still unbroken. There is a strange poetry in this, that the greatest force in the cosmos is the one we understand the least, that the destiny of all things is written in the language of ignorance. Dark energy is the shadow on the wall, the echo of an unseen presence, the silent hand guiding the stars. It is the reminder that in the end, the universe is not only stranger than we imagine, but stranger than we can imagine. Yet this ignorance is not defeat. It is the engine of curiosity, the spark that drives science forward. The questions we cannot answer are the ones that matter most, the ones that shape our understanding of everything else. In the darkness between the stars, in the spaces between galaxies, in the silence between questions and answers, there is the promise of discovery. In the deep future, when the last star has faded and the universe is an ocean of night, perhaps some distant intelligence will look back and marvel at the brief moment when the cosmos was young, when its mysteries still beckoned, when the question of dark energy was still open. Perhaps they will know the answer that eludes us now, or perhaps the answer will always be just beyond reach, a horizon receding faster than light. For now, we search. We build telescopes and accelerators. We map the sky and probe the vacuum. We imagine and we wonder. We live in a universe propelled by a force we cannot see, shaped by a darkness we cannot touch, destined for a future we can barely comprehend. And in that darkness, in that uncertainty, there is a beauty more profound than certainty, more enduring than knowledge. This is the story of dark energy, the force that accelerates the cosmos, the mystery that defines its future, the question that remains after all others are answered. It is the story of the universe itself, unfolding in darkness, racing toward a destiny written in the stars and in the silence between them. In the earliest days of cosmology, before the discovery of cosmic acceleration, the great debate centered on the ultimate fate of the universe. In the halls of academia and the observatories perched atop lonely mountains, minds like Edwin Hubble, Georges Lemaitre, and Subramanian Chandrasekhar contemplated the cosmic balance sheet. Would the universe expand forever, the galaxies fleeing eternally into the void? Or would gravity, the ever-present sculptor, eventually halt the expansion and drag all matter back into a final collapse? The answer depended on a single parameter, the critical density, the dividing line between eternal growth and ultimate return. The discovery of dark energy, however, upended this dichotomy, adding a new term to the cosmic equation. The universe was not merely expanding, it was accelerating, and the force behind this acceleration was of a kind never before encountered. The cosmological constant, once a mathematical curiosity, became the leading suspect, but its physical nature remained elusive. Was it a property of the vacuum, a remnant of primordial fields, or a sign of deeper physics yet undiscovered? To understand the stakes, one must delve into the mathematics of expansion. The Friedmann equations, derived from Einstein's general relativity, govern the evolution of the universe's scale factor, a measure of how distances between galaxies change with time. In their simplest form, these equations relate the expansion rate, the Hubble parameter, to the universe's energy content, matter, radiation, curvature, and dark energy. Each component dilutes differently as the universe grows. Matter thins out as one over the volume, radiation even faster as its energy is redshifted. But a true cosmological constant does not dilute at all. Its energy density remains fixed, no matter how far the universe stretches. This property has profound consequences. As the universe expands, matter becomes ever more rarefied, its gravitational influence waning. Eventually, dark energy dominates, and the expansion accelerates. The age of matter gives way to the age of dark energy, a transition that, according to current estimates, occurred around 5 billion years ago. Before this epoch, the mutual attraction of matter slowed the expansion. Afterward, the repulsive pressure of dark energy took over, and the universe began its headlong flight. Observationally, this transition is imprinted across the universe's structure. The pattern of galaxies, the clustering of clusters, the subtle ripples in the cosmic microwave background, all bear the fingerprints of dark energy's rise. The Sloan Digital Sky Survey, the Baryon Oscillation Spectroscopic Survey, and the Planck satellite have mapped these features with increasing precision, confirming the dominance of dark energy and narrowing the range of possibilities. Yet the physical origin of dark energy remains a riddle. To many physicists, the notion of a true cosmological constant is unsettling. Quantum field theory, our most successful description of the subatomic realm, predicts that empty space should be frothing with energy, virtual particles popping in and out of existence, fields fluctuating at every conceivable scale. The sum total of this vacuum energy, calculated naively, is staggeringly large, leading to a cosmological constant many orders of magnitude greater than what is observed. This discrepancy has been called the worst theoretical prediction in the history of physics, a sign that something fundamental is missing from our understanding. Some theorists propose that a new symmetry, as yet undiscovered, cancels most of the vacuum energy, leaving only a tiny residue. Others suggest that the cosmological constant is not a constant at all, but the average effect of a dynamic field, quintessence, slowly rolling down its potential, changing its influence as the universe evolves. If dark energy is indeed quintessence, then its equation of state, the ratio of its pressure to its energy density, should differ from -1, the value expected for a cosmological constant. Current measurements from supernova, galaxy surveys, and the cosmic microwave background are consistent with -1, but the uncertainties leave room for subtle deviations. The search for these deviations is a central focus of modern cosmology. The Dark Energy Survey, operating from Chile's Cerro Tololo, has catalogued hundreds of millions of galaxies, searching for signs that dark energy's grip is changing over time. The Euclid mission, launched by the European Space Agency, is mapping the geometry of the universe with exquisite precision, measuring the growth rate of cosmic structure and the bending of light by gravity. The upcoming Nancy Grace Roman Space Telescope, with its wide-field infrared eye, will probe even deeper, seeking the subtle imprints of dark energy on the arrangement of galaxies and clusters. If evidence emerges that dark energy is not a cosmological constant, the implications are profound. A dynamic dark energy could signal the presence of new fields, new particles, or new forces, perhaps connected to the early universe's inflationary epoch or to the unification of gravity with quantum mechanics. It could point to the existence of extra dimensions or to modifications of gravity on the largest scales. Each possibility opens a new chapter in the story of the cosmos, a new avenue for discovery and wonder. Yet the simplest hypothesis remains stubbornly consistent with the data. The cosmological constant, with its unchanging density and constant pressure, fits the observations as well as any more complex alternative. This simplicity is both a blessing and a curse. It offers a clear, predictive framework, but it leaves the underlying mystery unresolved. Why does the cosmological constant have the value it does? Why is it so small, yet not zero? Why did it come to dominate the universe's evolution only recently, in cosmic terms? These are the questions that haunt the theorists' dreams, the puzzles that keep the midnight oil burning in the world's great observatories and laboratories. The future of the universe, then, is written in the properties of dark energy. If it remains constant, the expansion will continue to accelerate, galaxies will drift apart, and the night sky will grow ever emptier. In the far future, the observable universe will shrink to a mere handful of galaxies, gravitationally bound and isolated, their stars growing cold and dim. The cosmic microwave background, once a brilliant afterglow, will fade into oblivion, its photons stretched beyond detection. The universe will approach a state of maximum entropy, a heat death, where all structure dissolves into randomness, and all energy is evenly distributed. But if dark energy changes, the outcome could be far stranger. In the phantom energy scenario, where the equation of state drops below -1, the acceleration becomes so violent that in time, even gravitationally bound systems are torn apart. Galaxies are shredded, then solar systems, then planets, then atoms. The very fabric of matter is unraveled in a final explosive, big rip. The timing of this apocalypse depends on the properties of dark energy, but in most models it is trillions of years away, far beyond the lifespan of stars or civilizations. Alternatively, dark energy could decay, fade, or reverse, allowing gravity to regain control. In this big crunch scenario, the expansion halts, then reverses, and the universe collapses back into a singularity, a mirror image of the Big Bang. Some theories propose that this collapse could trigger a new cycle, a big bounce, where the universe is reborn from its own ashes, endlessly repeating the cosmic drama. Each of these futures carries its own risks, its own poetic resonance. The Big Freeze is a slow, cold death, the ultimate entropy, a universe without structure or meaning. The Big Rip is violent and sudden, a last moment of drama before oblivion. The Big Crunch is a return to the beginning, a cosmic Ouroboros, endlessly consuming and recreating itself. The Big Bounce offers hope of renewal, but at the price of eternal recurrence. For now, the data points toward the Big Freeze, a universe accelerating into darkness, its structure unraveling over unimaginable timescales. The risks to human existence are abstract, more philosophical than practical. We are ephemeral, our lifespans a brief spark against the backdrop of cosmic time. Yet the contemplation of these fates shapes our understanding of meaning and mortality, of purpose and possibility. In seeking to understand dark energy, we confront not only the mechanics of the cosmos but the limits of knowledge itself. The mystery is as much philosophical as scientific, a challenge to our deepest assumptions about reality. Is the universe ultimately knowable? Are there truths forever beyond our reach? Is our ignorance a sign of failure or a testament to the boundless complexity of existence? The pursuit of dark energy is a testament to the human spirit, a refusal to accept ignorance, a determination to probe the darkness with every tool at our disposal. It is a journey that spans the globe and the centuries, from the ancient astronomers who mapped the stars to the modern physicists who seek the secrets of the vacuum. It is a journey that unites us across cultures and generations, a shared quest for understanding and meaning. The story of dark energy is not yet finished. New data arrives each year, new theories are proposed, new instruments are built. The Vera C. Rubin Observatory will soon survey the sky with unprecedented speed and depth, capturing the transience of the universe in real time. The Square Kilometre Array will map the distribution of hydrogen across cosmic history, tracing the growth of structure from the first stars to the present day. The James Webb Space Telescope, peerless in its sensitivity, will glimpse the earliest galaxies, searching for the fingerprints of dark energy in their arrangement and evolution. In the laboratories of Earth, new experiments seek to probe the vacuum, to measure the energy of empty space, to test the limits of gravity itself. The search for a quantum theory of gravity, a unification of Einstein's general relativity with the principles of quantum mechanics, could reveal new insights into the nature of dark energy, or even explain its value from first principles. The interplay between the smallest and largest scales, between the quantum and the cosmic, is at the heart of this mystery. The implications of dark energy extend beyond cosmology. If its properties can be manipulated or understood, it could open the door to new technologies, new forms of energy, new ways of manipulating space and time. The dream of harnessing the vacuum, of bending the fabric of reality to our will, is a distant prospect, but one that fires the imagination. Yet for now, dark energy remains the great unknown, the force that shapes our destiny, the question that defines our age. Its discovery was a shock, a reminder that the universe is stranger than we can imagine, that the story is not yet finished, that the greatest mysteries are still ahead. In contemplating the risks and futures of the cosmos, we are reminded of our place in the grand scheme of things. We are children of the stars, born of the same processes that shaped the galaxies, shaped by the same laws that govern the expansion of space. Our questions are the universe's questions. Our search for meaning is the universe's search for meaning. The universe is accelerating, driven by a force we do not understand. Its future is uncertain, its fate unwritten. But in the darkness, in the silence between the stars, there is the promise of discovery, the hope of understanding, the beauty of mystery. This is the legacy of dark energy, the force that accelerates the cosmos, the mystery that defines its future, the question that remains after all others are answered. It is a story of ignorance and discovery, of wonder and humility, of the endless quest to know the world and our place within it. And so we search, we build, we measure, we imagine. We look into the darkness and see not emptiness but potential, not an end, but a beginning. In the accelerating universe, in the mystery of dark energy, we find not despair, but hope. The hope that, in asking the questions, we become part of the answer, and that in seeking to understand the cosmos, we come to understand ourselves. As we look ahead, the canvas of the cosmos stretches before us, vast and unfinished. The fate of all things, of stars, of galaxies, of space and time itself, rests on the properties of a force we cannot see, a presence we cannot touch. The risks are existential, the possibilities infinite. In the darkness, in the silence, in the acceleration of the universe, there is a story still being written, a story in which we are both authors and readers, both question and answer, both observer and observed. And in this story, the greatest mystery is not the darkness, but the light we bring to it, the light of curiosity, of imagination, of wonder. The universe is accelerating, and so are we, racing toward understanding, carried by a force as old as time, as vast as space, as mysterious as existence itself.